If you guys are satisfied, you don't have to stay here, you can go. But if you need to go back over this stuff, then I'm happy to do it with you. So problems 1 and 2 here are about percent composition chemical formula, and they refer to page 282. And so I'm going to write them out, show them how to do it. So the first one is copper bromide. There's one copper, Cu, and there's one bromine, Br2. So I need the mass of one copper, which is just Cu. I'm going to need the mass of 2 bromines. And then for the one that comes afterwards, we're going to have sodium hydroxide. And for that, I'm just going to need 1 sodium, 1 oxygen, and 1 hydrogen. So I'll do both of those about the same time. Okay, so this is problem 1, this is problem 2. So if we look, 1 copper is 63.546 grams, and 2 bromines is 2 times 79.904. It works out to be 159.808. So this is the contribution in mass by copper, about 63, and this is the contribution by the 2 bromines, about 159. We add them together, it's 223.354. So what we're going to do is we're going to take the contribution of the copper divided by the contribution of the total, which of course is 63.546 grams divided by 223.354 grams. We're going to do the same trick with the 2 bromines. Divide those 2 masses by the molar mass. Now if we do that, we get decimals, and the decimals thankfully are numbers less than 1. Both these numbers get multiplied by 100 because that's what we do to the decimals in percent problems. And if we get done doing this, we discover, well, this is 28.5, I'm rounding up, percent copper. It's 71.5% bromine. So that's that problem. Now for problem 2, we have 1 sodium, 1 oxygen, 1 hydrogen, and so this is 22.990, and this is 15.999, and this is 1.008. And if we add them all together, we get 39.907 grams. So we do the same trick. We divide sodium, oxygen, and hydrogen by the total for each one. So these are not hard, but they're just time consuming. And if we do the math, we get 3 different decimals, which when multiplied by 100 gives us 57.4% sodium and 40.1% oxygen and just 2.5% hydrogen. Now the next problem we're going to do is one that's going to involve a 2-step conversion. So once again I'm going to draw a flow chart. We put moles in the middle with a double arrow on 3 sides. So if we want to go from moles to grams or grams to moles, what do we use? We use the molar mass as our conversion factor. And if we want to go from moles to liters or liters to moles, we use the molar volume, which is 22.4 liters per mole. And if we want to go from moles to particles, the actual number of particles, well, that's where we're going to use Avogadro's number, 6.02 times 10 to the 23rd. We can see this on the screen. Problem for number 3. Calculate the number of atoms in 0.034 grams of zinc. So the grams of zinc is our given, like so. We're going to take the molar mass of zinc, which we just get directly from the periodic table, If you have 1 mole of zinc, you have 65.38 grams of zinc. Now, of course, we can cancel the grams of zinc out, and if we stop here, we end up with an answer in moles, but they don't want that for problem 3. For problem 3, they want the answer to be the number of molecules, and so we have to add a second step, a second conversion factor, and that conversion factor is Avogadro's number. If you want to know the actual number, you need Avogadro's number. So if you have 1 mole of anything, you have 6.02 times 10 to the 23rd of that something. So now that we have this set up, we can cancel the moles as well. And so this becomes 0.034 times 6.02 times 10 to the 23rd, which gives us a fairly large number. So sorry. And we now divide that large number by 65.38. And if we do, we get this answer, 3.13 times 10 to the 20th atoms of zinc. All right, moving now to problem 4. How many liters of 0.88 molarity solution can be made from 25.5 grams of lithium fluoride? It says, remember to convert grams to moles on page 274, then go to page 277. So what is given here first is the 25.5 grams of lithium fluoride. That's our given. So we'll write that first, 25.5 grams lithium fluoride given. Now referring to our flow chart, we want to get this to liters. Specifically, we want to know the number of liters, and here it's not an STP problem. We're going to get liters not from our conversion factor here. We're going to get it from the definition of molarity. Because what it wants to know is it wants to know how much of a particular concentration. It wants to know if the solution is this molarity. It wants to know how many liters you're going to have. We're taking this solid amount and we're going to dissolve it in a certain amount of water. And the question is, you know, how many liters of solution can we make if we end up with a concentration of 0.88 molarity? Well, to understand this, we got to remember that molarity just means moles per liter. If I say 0.88 molarity, that means 0.88 moles for 1 liter. So obviously I somehow have to get to moles. So I'm going to need the molar mass of lithium fluoride. Lithium is 6.94 and fluoride is 18.998. So if we take those two and add them together, the molar mass of lithium fluoride is 25.938. So that's straight from our periodic table. So if I have 1 mole of lithium fluoride, I've got 25.938 grams of lithium fluoride. Now you will notice that this is very close to the actual given amount of grams. It's just a little bit more, and that might freak you out, but don't let it. It's just what's going to happen. Okay. Now, of course, if we do this conversion factor, the grams of lithium fluoride are going to cancel. Now, at this point, you might be tempted to say, okay, I went grams to moles. Now I'm going to go moles to liters, but you don't actually have to use this. This is only for predicting the number of liters at STP. We don't actually need to do that. Why don't we? We can get there by using the definition of molarity. We know our solution has to be 0.88 molarity, which means it's got to be 0.88 moles per liter. Since I've got moles of lithium fluoride here on the top, I need 0.88 moles. Wow. I need 0.88 moles of lithium fluoride on the bottom. And our definition says 0.88 moles per liter, so I just need 1 liter solution here on the top. moles of lithium fluoride will cancel. And so we're going to take that 25.5 and we're going to divide it by the product of these two numbers, 25.938 times 0.88. And when we do that, we're going to get 112, well, not 112, sorry. We're going to get 1.12 liters of 0.88 molarity lithium fluoride solution. That's your answer. That's number 4. Now, number 5, it's super simple, and they make it hard just by the way they ask it, I think. So let's take a look at that question. What's the molarity? Remember, molarity is just moles per liter. And they make this hard because they're giving you information, but you can't use this information right away. They say that you're going to have, this is number 5, you're going to have 100 milliliters of some stock solution. You're told that it's 0.15 molarity. So you know the molarity of this solution, which by the way is sodium hydroxide, NaOH, and you got 100 milliliters of it. Okay, that's the stock solution. And they want to make a dilute solution. The dilute solution is going to be 150 milliliters, and they want to know what's the molarity. So it's actually not, it's not obvious what's being given here first to solve. Okay, so again, you start off with 100 milliliters of stock solution, which is at 0.15 molarity sodium hydroxide. That's what it is. We want to end up with 150 milliliters of dilute solution. We want to know what the molarity is. Well, this is a pain in the neck because molarity is moles per liter. It's not moles per milliliter. So we have to take the numbers in, the numbers for milliliters here. We got to take this number and, well, we got to convert it into liters. So the way we do that is we use the fact that there are 1,000 milliliters in 1 liter. You just divide by 1,000. And so it turns out that this is 0.1 liters. Okay. Now, once we know that 100 mils is 0.1 liters, we can use the molarity to figure out how many moles are there. Because, again, molarity just means moles per liter. So I've got 0.15 moles of sodium hydroxide per 1 liter of sodium hydroxide. And you can see how very nicely, how the liters will cancel out, right? So again, first we converted the 100 mils into liters. Now we're multiplying, instead of 100 milliliters, we're going 0.1 liters times molarity. And liters times moles per liter, the liters are going to cancel out, and our answer will be moles. And then what are we going to do here? Well, that means let's just do the math. We do the math, we determine that this is 0.15 moles. And we just want to figure out what the molarity is. It's just moles per liter. So what is the number of liters going to be? Well, we start with 100 milliliters with the stock, but we're going to make 150 milliliters of the dilute. In other words, we're adding 50 milliliters of water. But the total amount of fluid that's going to be used to dissolve this many moles of solid is 150 milliliters. But again, we can't do moles per milliliter. Molarity is in moles per liter. So I got to convert that 150 milliliters. How do I do it? Well, again, I'm just going to divide by 1,000. I'm not going to even do that calculation. If 100 divided by 1,000 is 0.1, then 150 divided by 1,000 is 0.15. And I just put it there right that because molarity is just moles per liter. And if we do the math, guess what? This is a 0.1 molarity solution. So before it was 0.15 molarity, and now it ends up as 0.1 molarity solution. They make it way harder than it needs to be because they just assume that students know that milliliters are, that 100 mils is 0.1 liters, and they just assume students will do that. And if students haven't memorized this conversion factor, then they won't have things in liters, and their answer will be off. And 6, has a lot of steps, but it's basically to get the molar mass, you divide it by the number of moles you get by the liters, and you end up with a molarity, just like this problem, just the same. What does it say? Calculate the molarity in a solution containing 40 grams of sodium chloride dissolved in 500 milliliters of water. So I've written it out here. Again, 40 grams of sodium chloride dissolved in 500 milliliters of water. What's the molarity? Let's make our lives really easy. Let's just remember that this is going to be liters. It's going to have to be liters because we need to get things in moles per liter because that's the definition of molarity. If we want to find the molarity moles per liter, this has to be in liters. So we're just going to divide that by 1,000. And so this is just going to be 0.5 liters. Oh, this is going to make our life so much easier. Okay, so we take our given, which is 40 grams of sodium chloride. That's what's given over 1. And we're going to convert it from grams to moles because we got to have moles in order to do moles per liter. So we're going to use the molar mass. It turns out that 1 sodium is 22.99 and 1 chlorine is 35.45, and we add them all together. Hey, 1 mole of sodium chloride is 58.44 grams of sodium chloride. So this result will give me the number of moles, which is 0.6844 moles sodium chloride. And now all we're going to do is we're just going to take that 0.5 liters and we're going to use that to calculate the molarity. There it is. So again, we were given 40 grams of sodium chloride and 500 milliliters. You know, what's the molarity of this solution? We just went ahead in our heads and converted the milliliters to liters by dividing it by 1,000. So now it's going to be 0.5 liters. We'll come back to that. We take our 40 grams and using the molar mass in the periodic table, we convert it into number of moles. Now we know the number of moles. We've already determined that it's 0.5 liters. So that many moles divided by that many liters gives us a molarity of 1.37 moles per liter. And that is all she wrote for problem number 6. 7 says, what is the molecular formula if the empirical formula is CH2 and the molecular molar mass is 360.36? And they refer you to page 289. What is the molecular formula? Okay, so the molecular formula is the actual number of each element. Like, for example, if CO2 is your molecular formula, it means you've got 1 carbon and 2 oxygens. As H2O is your molecular formula, you've got 2 hydrogens and 1 oxygen. Here, we have what's called an empirical formula. So what's the difference? Well, the empirical formula isn't necessarily the actual number of each element, it's the proportions. So if we say that the empirical formula is CH2O, that means that we have a ratio between these 3 elements. So going back to my screen, if we say that the empirical formula is CH2O, all we know is, we don't actually know the formula yet, all we know is that there's, for every carbon, there's 2 hydrogens and 1 oxygen, that they occur in this proportion. So this is the so-called empirical formula. It's not an actual formula, it's just a relationship. Now what we want to do is we want to determine what the actual molecular formula is. The actual molecular formula is something different. So how do we determine it? Well, our first move is we're going to need to get the molar masses based upon this. This is not the actual formula, but this is their proportions. And so just as there's a proportion for the number of each type of atom, there's also a proportion in mass, because 1 carbon, and I get this from the periodic table, 1 carbon is 12.011 grams. We need 2 hydrogens in this setup, so 2 hydrogens is not 1.008, it's 2.016 grams. And then 1 oxygen, as always, is 15.999 grams, okay? So we just want to get the relative masses. This is the relative number we find from the data, and this would be their relative contribution to mass. Okay, so if we take the numbers for carbon, the 2 hydrogens, and the oxygen, we still don't know what the actual formula is. Oh, that was awkward. We still don't know what the actual formula is, but we know that the total mass of what the proportions are gives us this, 30.026 grams. The original problem. Okay, the original problem says, what is the molecular formula? We're trying to find the molecular formula, the actual arrangement of the atoms. If the empirical formula is CH2O and the molecular molar mass is 360.36, okay? So we do have a mass in grams for this substance. We've determined its molar mass, and we see that the carbons, hydrogens, and oxygens exist in a 1 to 2 to 1 ratio, but we don't actually know what the formula is. And so this is kind of interesting math, because you can actually take a sample and figure out that 1 mole is a certain number of grams, but you might not know what the substance is. You've just figured out, hey, there's carbon and hydrogen and oxygen in there, and 1 mole is going to weigh this much. Question is, how many carbons are actually there in each molecule? How many hydrogens are actually there? How many oxygens are actually there? So that's what we're trying to do. We're trying to take an abstract relationship and actually determine what's actually there. Okay, so that being said, we're now going to take the individual contributions that we have here, and what we're going to do is we're going to take that number it's given about the molar mass that's known. The molar mass is known, we just don't know what the substance is. That's kind of weird, but yeah, okay. So we're going to take that number that they gave us, 360.36, and we're going to divide it by the mass of these items together. And when we do that, look carefully. You're going to get a number that's almost perfectly 12. It's not quite 12, it's a little bit more than 12, but you can see it's almost 12. So we refer back to our original formula. The empirical formula was so, and again, that just means that there's a 1 to 2 to 1 ratio, all right? So, but it looks like there's 12 units in there. So we're going to take everything here and multiply everything by 12. So if we do that, we'll end up with 12 carbons, 2 times 12, 24 hydrogens, and 12 oxygens. And that is the actual answer. Okay, so let me turn that off. There's some glare there, okay? Again, what would happen was we were given, this was the empirical formula, which is just a ratio, 1 carbon to 2 hydrogens to 1 oxygen. And so we take it seriously, that estimate. We take it seriously, and we add it together. And so 1 carbon, 2 hydrogens, and 1 oxygen would weigh just 30.026 grams. We use that to divide the molar mass, and we determined that it almost goes in evenly, almost exactly 12 times. So we go back to the original formula, and we multiply everything by 12, and this is our prediction for the actual molecular formula. Okay, so I'll give you about, I don't know, 20, 30 seconds to copy that down before we go on to our next problem, problem number 8. Okay, so let's go back to it. If you just joined us, we are reviewing problems that appear on a practice test, which is available to all students at the very bottom of your team's channel. Just find the latest post and click on where it says practice test, download it to your own computer, and then follow along, copy along the problems as we do them. Okay, so this problem says that we've got a molecular formula. We want to find the molecular formula. And again, we know the molecular mass is about 696 grams. And we are told that the empirical formula is K2SO4, right? If it were K2SO4, that would be potassium sulfate. 2 potassiums, 1 sulfur, and 4 oxygens. Well, we don't actually know what it is yet. All right, so let's pretend that we don't know what it is. And again, the formula we're given says K2SO4, okay? And what this means is we have a relationship between potassium, sulfur, and oxygen. The relationship is for every 2 potassiums, you've got 1 sulfur, and you've got 4 oxygens. Now, that's not the actual number yet. It might be, but we don't know that yet. We don't know. It's just a relationship. Okay, but we're going to go ahead and figure out what the relationship is. So 2 potassiums, that's 2 times 39.098. So we do that, and that turns out to be 78.196 grams. Again, all these numbers are coming from the periodic table. And 1 sulfur is just 32.06. And then we have 4 oxygens, and that's 4 times 15.999, which turns out to be 63.996. Okay, so we're going to add them all together, and when we do, we get this number, 174.252. Now, just like before, we're interested in the question of what is the true formula? So we're going to take the mass that was given. We were told that there was 696 grams in the total mass. And we're going to divide that by the number we got by taking the individual masses of each group of atoms. We're going to do that. Now, when we do that, and I think this is, you really have to be careful here. You have to do some thinking. So let me just put those numbers in so you can see. 360. I'm sorry, that's the wrong number. 696 divided by 174.252. Now, when I do that, I am not getting a nice round number. The other example, I got 12.001. It was very obvious. Well, this one I get 3.9942, blah, blah, blah. It's actually a little bit more than 3.99, but it's not 3.9. So you have to think here, but you should realize that this is approximately equal to 4. So our best guess is that we're going to take this entire thing, K2SO4, and we're going to multiply each part by 4. 2 potassiums would become 8. Oh, wow, terrible. 2 potassiums would become 8. 1 sulfur would become 4. And the 4 oxygens become 16. And that is our answer there. I'm going to turn off the little glaring. So problems 7 and 8 are both the same kind of problem. You're taking what's called the empirical formula. But the empirical formula isn't actually a formula. It is a ratio based upon actual data. People don't actually know what the formula is. They just know, they've just figured out that you've got, you know, the numbers are in this ratio, roughly. That you have roughly 2 potassiums to every 1 sulfur to every 4 oxygens. Now from that, you take the individual contributions of their mass and add them all together, like that was the actual formula, and you have it come up with an estimate in grams. You use this estimate to divide the actual molar mass in grams. You'll get typically a number that's not perfect, but it'll be a decimal. Here's 12.001. Here it's 3.9942, and you just have to reason that 12.001 is effectively 12, that 3.9942 is effectively 4. You have to round it to the nearest whole number. And if the setup is good, it should be very, very close to the number you want. And then you take that number and you simply multiply that number by the empirical formula, which is just a ratio, the data that you got, and this becomes your guess, your best guess at the actual molecular formula. So these things are empirical formulas which are really not formulas at all, they're just ratios. This is the actual best guess at the molecular formula, the actual number of each type of atom that's in the actual compound. Okay, I'm going to leave 7 and 8 up for about 30 seconds or so before I go on. Problems 9 through 12 start having more steps, and I need more room, so if you need time to copy them, that is fine. Now again, if you've just joined us, we are working our way through problems that appear in a practice test, which I've inserted into the end of every class's Teams channel. So if you don't have these problems in front of you to refer to, you can go and get them by downloading that document and opening it on your own computer. And then what I'm going to do is I'm working my way through the problems. I've just worked through the first 8. And I want you to copy along and copy down what I do to work the problem, because there are going to be problems just like this on the test. I'm not taking a grade. I'm just showing you step by step how you would approach doing those problems. Okay, so I'm going to erase 7 and 8 in a moment, but I'm now going to go and we'll take a look at number 9. Number 9. What is the empirical formula if you have 81.82% carbon and 18.8% nitrogen? So here, instead of giving us the empirical formula, they're asking for it. And here, in other words, they're asking us to come up with a ratio. This is not going to be like doing a molecular formula like H2O or CO2. This is going to be a formula that's actually just a ratio, a best guess based upon the fact that you've measured a sample and you've determined that it's a certain percentage of one element, carbon, and another percentage of another element, hydrogen. So if you're wondering how we get these estimates for the ratios, this is an example. We've got some substance, and our analysis says it's 81.82% carbon, and it's 18.18% hydrogen. So what's our guess as to the empirical formula? How many carbons, how many hydrogens? All right, so that's what we're doing. Now we're basically coming up with a ratio. Okay, so again, this is number 9. Number 9. All right, so we are told that we have 81.82% carbon, 18.18% hydrogen, and we want to know what is the empirical formula. Okay, so what we're going to do is we're going to take the percentages and we're going to treat them like they were grams. So I'm going to say 81.82 grams of carbon, but I'm going to divide that by the mass, the molar mass of carbon from the periodic table. I'm going to do the same trick with hydrogen. I'm going to take that percentage and I'm going to turn it into grams. And I'm going to divide that by the molar mass of hydrogen from the periodic table. Okay, so I'm just treating the percentages like they were grams. Now, why does this work? Well, let's say I had 100 grams. If I had 100 grams, then I'd have 81.82 grams of that would be carbon, and 18.18 grams of that would be hydrogen, and it adds up to 100. That's why this will work. Okay, so if we do that, if we do the math, and keep in mind this is grams and this is grams per mole, this becomes an estimate of how many moles we have. Right? Because this is actually grams per mole. So if we do this math like this way, we get this estimate that there are 6.812 moles of carbon. And we do the same stunt here with the hydrogen, dividing it by the molar mass of hydrogen. Again, the grams will cancel out, and we'll get this estimate that we have 18.04 moles of hydrogen. Now it's not perfect, but that's an estimate. If we had a 100-gram sample, then 81.82 grams of that sample would be carbon. If we divide that amount by the molar mass of carbon, it gives us that many moles. And it would be this amount would be grams of hydrogen divided by its molar mass. We get this many moles. Now, obviously, these are not whole numbers, right? I can't, okay, I'm not going to write carbon 6.812, hydrogen 18.04, okay? That is not the case, because we're not going to be talking about moles. We want to know how many number of atoms, and the atoms don't come in decimals. They come in counting numbers, right? Not in decimals, not in fractions. There's no such thing as 1/2 of a proton. There's no such thing as 0.378 of a neutron. Okay, they have to come in counting numbers. Okay, so what do we do? Well, the number for carbon, the number of moles for carbon is smaller than the number of moles for hydrogen. So what we're going to do is we're just going to divide both sides by 6.812 moles. Now, when I do that, of course, that'll all cancel. This, of course, is just 1. The number for carbon is just 1. And if I do it for hydrogen, I get about 2.6 for hydrogen. Now, if I did the actual math, just to be clear, 18.04 divided by 6.812, okay, take a look. I don't actually get 2.6 on the nose. I get 2.64. If we wanted to, we could round this differently. But I'm just gonna go ahead and round it like this. Because my goal is to come up with a ratio, a whole number ratio. I want both carbon and hydrogen to be a whole number. Right now, carbon's a whole number, but hydrogen's not. Okay, so this 1 carbon for every 2.6 hydrogen are our molecular formula. I have to somehow get it where it's in whole numbers. So times 1 doesn't work. So what if I go times 2? If I go times 2, well, then the 1 of carbon will become 2. And that's a whole number, so that's okay. But 2.6 won't become a whole number. That'll become 5.2. So 2 doesn't really work. But if I take 3, I get 3 carbons, and I get 7.8. I get 7.8. Probably should stop here and just go back, and I should probably just be a little bit more precise, just so you can see how this works out. So, because I actually rounded as a step. This actually is 2.648. So if I go that times 2, it's 96. It's still not good, but you know, it is what it is. But if I take the same number, 2.648, and go times 3, I get this. That is very, very close to 8. And that is within 5% of 8. It's very close. So we're going to say that this is approximately 8. And so our guess for this compound that is made of carbon and hydrogen, our guess is that the formula should be C3H8. 8 carbons and almost precisely 8 hydrogens. Now, is it completely satisfactory? It is not, but we didn't actually measure this to perfect accuracy either, and so you have to watch out here. This is a case where rounding rounding a number too much, even if it's more accurate for the sake of measurement, it will lead to confusion. Okay, so I'm just going to pause there for a moment. A percent composition problem where we're given the percent and you're asked to figure out the empirical formula. You're asked to figure out, this is just a guess, an empirical formula. It's not the actual molecular formula, but it's very close, very close. Okay, I'm just going to, problem 10 is a doozy. It's got multiple parts, it has extra steps, and because that's the case, I'm going to pause. I'll give you the chance, pause here, give you the chance, so if you haven't had this copied down yet, you can do so, and then I'm going to go on, but I'll probably need most of the screen to do problem 10. Problem 10 is the same kind of problem, except instead of one substance, it involves two substances. And the two substances are products of a chemical reaction. The two substances are going to be carbon dioxide and water. And so, since the products are carbon dioxide and water, we actually know what kind of reaction it is. It's what's called a combustion reaction. In combustion reactions, we have often have simple compounds that are made of carbon, hydrogen, and oxygen, and they react with oxygen in the air, and we always get the products water and CO2. And it's a basic concept. It's the kind of reaction that we like to keep track of. So here's the problem. It says 225 grams of an unknown compound is burned, which releases 287 grams of CO2 and 147 grams of water. Now you may say, well, wait a minute. You only started off with 225 grams and you're getting 287 grams of one thing, you're getting 147 grams of another thing. Where's all that matter coming from? Well, the answer is it's coming from the atmosphere. We're burning an unknown compound, but combustion reactions they react with oxygen in the atmosphere. So what we're going to do is a very cool trick. We're going to figure out how many grams we got of this unknown compound, and we are going to figure out what its empirical formula is likely going to be based not upon the actual compound itself, but upon its products. But that means we're going to have a setup for one product, carbon dioxide. We're going to have a setup for another product, water. All right, so again, it's got extra steps. So here we go. Problem number 10. Okay, so first piece of information, we have 287 grams of CO2. And we also have 147 grams of water. Again, these are the products of the reaction. And what we're going to do is we want to figure out the molecular formula from these products. So to do that, we're going to need some molar masses. One molar mass we're going to need is the molar mass of carbon dioxide. One carbon, which is 12.011, and the two oxygens, which are about 37.99 grams. So if we do the math here, it turns out that for every mole of CO2, we're going to have 44.009 grams of CO2. So on our flow chart, we're starting with grams, and we're converting to moles. But we have to do it for both substances. Some of you may have already memorized the fact that one water, H2O, two hydrogens, and one oxygen, has a molar mass of 18.015 grams of water. All right, so that's our setup for that. Let's go ahead and cancel the grams. And this is just division. And when we get done dividing, we have 6.52 moles of CO2. And we have 8.16 moles of water. Okay. Now these are moles of these substances. And what we have to remember, if we have these, we have certain things are true. If I've got 1 mole of carbon dioxide, that means I've also got 6.52 moles of carbon. But I've got 2 times 6.52 moles for the oxygens. I have 2. So there's actually that many moles of oxygen in that mole of carbon dioxide. Same thing's true for the hydrogens in water. If I've got 8.16 moles of H2O, I've got 2 times 8.16 moles for the hydrogens. So that's 16.32 moles of hydrogen and 8.16 moles of oxygen. Okay. Now what I got to do is I got to recognize that I actually have 2 sources of oxygen. These aren't, before the chemical reaction happened, these many oxygens had to be present. So I got to add those 2 together, and it turns out that that's going to be 21.2 total moles of oxygen. Okay, so now I'm ready to do some math as far as the relative numbers of all the substances here. So my smallest substance is actually the moles of carbon. So I'm just going to have, if I divide 6.52 by 6.52, that's just going to be 1. So the number of carbons is just 1. But if I take the 16.32 moles of hydrogen and divide that by 6.52, well, I get a number that's about 2.5. And if I take the combined 21.2 moles of oxygen and divide by 6.52, well, I get a number that's about 3.25. So those are the ratios, but I need to get them into whole number ratios. You might think, okay, well, 2.5 times 2. If I multiply everything times 2, then carbon becomes 2, and the hydrogen 2.5, that becomes 5. That's a whole number, but the oxygen is still a decimal, so 2 is not going to do it. I go times 3. Well, that's actually worse. They're both decimals, so I'm going backwards. If I go times 4, I've got 4 carbons, I've got 10 hydrogens, and I got 13 oxygens. And so our empirical formula for all this matter is C4H10O13. We'll just stop there and say that this is our estimate based upon the data of the empirical formula. So problem 11 simply says, if a sample of lead-4 sulfite has 2.65 grams of sulfur, how many grams of sample are there? That is, if we know how many grams of sulfur we have, how many total grams we have for this formula, then we're given Pb SO4 inside parentheses 2. And so you'll notice here I've got a list of pages you might want to refer to. First, the molar mass, because you're going to need that first on page 267. Then percent composition from chemical formulas on page 282. And then page 284, where we're going to use percent composition as a conversion factor. We're asked to figure out PB SO4 inside parentheses 2. So let's make sure we understand what's going on here. Whenever we have a parentheses, you're expected to know that there should be a number on the outside of the parentheses. If there isn't a number, something bad happened. You should not try to solve a problem if there's with parentheses, if in the formula, if there's no number outside the parentheses, because there's no reason to have parentheses without a number. So what does the number mean? It's simply a multiplier. So here there's one lead, PB is the symbol for lead. And there are 2 times 1 sulfurs. So we're going to need 2 sulfurs, and then we have 2 times 4 oxygen. So again, whenever you have the parentheses like this, there should be a number on the outside. The number on the outside is a multiplier. You've got to remember to multiply that. So what is it? The mass of lead, 1 mole by itself, is quite a large number because lead is famous for its density. Sulfur is 32.06, so 2 times sulfur is 64. Times 15.99. In the problem, we're told that we have 2.65 grams of sulfur. So that's our thing that we're focusing on. We need to know the percentage of sulfur. So the percentage of sulfur, we don't have to know all the elements, we just have to do sulfur. The percentage of sulfur in this is this number, 64.112, divided by the mass of the total, which is 399.312. These are both numbers in grams, and the whole thing's going to be multiplied by 100. And if we do that, we get this number, 16.05% sulfur, okay? Now what's interesting is that we can now use this, we can use the decimal version of this as a conversion factor. Because 16.05% just means we've got 16.05 grams out of every 100 grams. That's all it means. I got 100 grams of lead sulfate, this compound, 16.05 grams of that is going to be just, sulfur. So we're told that we have 2.65 grams of sulfur. That's our given, over 1 inside parentheses. Since grams of sulfur is given on the top, we know we're going to have grams of sulfur on the bottom. We're going to be using the molar mass to go from grams to moles. And in this case, instead of using the molar mass, now we're going to flip the script, and we're just talking about the percentage, and the percentage says 16.05%. So if I got 100 grams of this, if I've got 100 grams of this substance, I'm not going to write PbSO4 I'm just going to write SUB substance. This is the substance, lead sulfate. I'm just going to say 100 grams of sub. That's 100. For every 100 grams of substance, I should have 16.05 grams of sulfur. Again, if sulfur is 16.05% of this compound, then if I have 100 grams of that substance, I'm going to have 16.05 grams, period. And so the grams of sulfur cancel out. And we do the math, and what we discover is, and the way they did this is tricky. I think Mr. Fisher designed this problem. He designed it so that the number that came out looks like the number we put in. And it's kind of deliberately designed to deceive you. Sorry about that. But 16.5 is not the same thing as 16.05. That's just the way the numbers have been rigged to come out. So it's kind of cute. But that's actually the solution. Again, what were you asked to do? You were told that you had this compound, and you were told that you had 2.65 grams, and you want to know if you had 2.65 grams of sulfur, what's the total mass of the compound? And so what did we do? We first got the molar mass of the whole compound. We used it to divide the percentage of the mass that's caused by the 2 sulfurs. We determined the 2 sulfurs mean that 16.05% of the total mass has to be due to sulfur. Then we take 2.65 grams of sulfur, and we use the fact that this is now, we've turned this percentage into a ratio. And so for every 100 grams of substance, we would have to have 16.05 grams of sulfur. The grams of sulfur will cancel out, and well, we end up with this prediction that if 16.5 grams. Now, if you didn't know if this looked weird to you, you could check it. You could say to yourself, well, 16.5 grams of the substance, and you could just take this conversion factor and flip it. For every 100 grams of substance, you've got 16.05 grams of sulfur. Grams of the substance would cancel out. Now let's do the math. And what does the math say? The math says that 16.5 times 16.05, and the whole thing divided by 100 is 2.648, which is the same pretty much as 2.65. And so you know you did it right.